Now we are going to design of the column. In the previous step, we already uh, determined the moment at every section of the frame, and we also determine the member force of each member, columns and beam. And beyond that, we can design the column. So as you can see here, there are two columns. The moment is same. Okay, the requirement moment is same, but the action force is different. So we will use the column with a higher action force for design. Okay, so it means we use this resolve for the further step of design this column. Okay. The requirement of moment capacity can be calculated by using this equation. M requirement equal to Mx plus P multiplied by D divided by 2. Actually, this is this part. This is MP, okay, equal to the requirement plus this one, and P is this here, action force, and D divided by 2. Now, actually, this is the empirical equation, okay, empirical equation. Based on the experience of researcher, then they propose this equation to determine the requirement of the moment. And here D is the height of the section. Okay, so for example, I section, then the length of section, the height of section is D. Okay, D. Then because that we can assume D. We assume D equal to 18 inch. Then we have M requirement equal to, it is MP or Mx. Okay, multiply by action force here, action force, and multiply by this one. Okay, and here's D. Then the requirement M equal to 299 kV. Then beyond this requirement of plastic moment, you has requirement of section modulus. G equal to M divided by pi b and Fy. Okay, and pi b equal to 0.9. Safety factor, and Fy equal to 36. And here's ME, requirement M equal to this one, and 12 is factor transfer from fit to keep. Okay, and finally we have Z equal to 112, 11 inch. Then beyond this requirement of section modulus, then we can try. You can check in the manual, and you can try different section. Okay, and the design, I recommend you to try with some different section. Okay, and then check different section to find the best section. In this example, we try with this section. This section has A equal to this and Z equal to this, and it is greater than the requirement. Okay. What else? And with this section, we have x equal to this and y equal to this. And now we have pi b theta, pi b and p equal to 0.9 multiplied by this one, okay, multiply by fy, and divide by 12, equal to this one, We check the stiffness ratio lambda cx equal to this equation, okay, and I also already explained this equation. And if you don't understand this equation, the meaning of this equation, so please check. Please back to the previous lecture and see what is meaning of this equation. Okay, so lambda cx equal to this, and we assume k equal to 1, and L is the length of the column. We already have x and fy and e, and replace the value of each factor to here. Then then we can determine lambda cx equal to 0.272, and it's smaller than 1.5, and it's okay because of plastic design. And similarly, we have lambda cy. Lambda cy equal to this one, and equal to 1.209, and again is smaller than 1.5, and it's okay for plastic design. And because of plastic design, okay, then this equation is U. Okay, for plastic design, we use its equation to calculate Mn equal to 0.658 lambda c square and py. You already know so this equation, and just replace the factor into here. Then we have Pn equal to this value. So we have theta pi theta b and m p equal to previous one. Please remember, or you can back and check the value. And now we have Pn equal to this one. And what else? P over pi c Pn. Because of the column, then we have 0.85. Okay, then Pn is just here, and P the action force in the column. Then we have resolve a reverse step. Then finally we have this ratio equal to 0.273, 8 greater than 0.2. Then the following equation is U for checking the condition. Okay, because of this ratio greater than 0.2, then this equation is U. And we already mentioned also this equation. Why we use this equation, how in the previous class. Okay, if you confused, then please check in the previous class. Okay, back to this problem. We have this equation to check, and we already have this one equal to here, and we have this value. Okay, then we can check M. From this one, we have m equal to this one also already, and the value of beta pi b and p equal to this one in the previous step. And finally, this ratio equal to 0.991 and is smaller than 1. It's okay. So our section is okay. Then we use this section. Okay. So this is final solution of the design of the column. Okay, the section of the column. So I've just finished a procedure of the design of a photo frame. Some equation is already mentioned in the previous class, and some new concept of today class. So we can use of them, both of them, for design of a structure. Next, we are moving to another new content. It is combination of mechanisms. Okay, combination of mechanism. First, we start with the number of independent mechanism. Number of independent mechanism. We have equation small n equal to upper n minus r. Okay, n equal to big N minus r. What is n? The big N is number of critical sections where plastic hinges might form. Okay, n equal to it is a number of critical sections where plastic hinge might form. And what is R? R is degree of redundancy of structure. Okay, R is degree of redundancy of structure. For example, if we have a photo frame like this under apply load here, vertical and horizontal, and MP equal to this one, for example, no problems. Then for a structure, what is N? N is number of critical sections where plastic hinges might form. So how many sections that plastic hinge might form? 1, 2, 3, and 4, and 5. Okay, so we have N equal to 5. How about R? What is the degree of redundancy of structure? Is it 3? Right? Yeah, it is 3. We already know the degree of redundancy of this structure is 3. We have 3 redundancies. Then n equal to 2. Okay, n minus 3 equal to 2. What does this mean? The number, sorry, lights turn off. Okay. For this structure, for this frame, okay, the number of independent mechanism is 2. So we have 2 independent mechanism. Okay, for 2 independent mechanism of this structure. Second, type of mechanism. Types of mechanism. How many types of mechanism and what type of mechanism we have? First, we have beam mechanism. Okay, beam mechanism. For example, if we have the previous structure, okay, it is original structure. Then the beam mechanism like this. If the load is here, okay, then the plastic here, plastic hinge is here, then this is beam mechanism. Beam mechanism. Okay. The second one is panel mechanism. Panel mechanism, or another word is sway mechanism. For example, the previous structure, okay, it is original structure. Then the panel mechanism is like this, okay. Then it is plastic hinge, and plastic hinge here, and plastic hinge here. Then we have sway mechanism or panel mechanism, okay, panel mechanism. The next mechanism type is joint mechanism. Joint mechanism. What is joint mechanism? If we have a joint, for example, like this, okay, a joint here, then the joint mechanism may be like this. Okay, so this is plastic in here, and plastic in here, and plastic in here. Okay, so this is joint mechanism. Sometimes we use this joint mechanism for analysis. Original one. This is original joint, and this is mechanism, joint mechanism. Okay, and the last mechanism types is combined mechanism. So let's say the three mechanisms is also called the independent mechanism. Okay, they are independent mechanism. Then this one is called combined mechanism. Okay, combined mechanism. Sometimes it is a portal mechanism. It means we combine two mechanisms together, then it is portal mechanism. And sometimes we combine all the mechanism together, then we have full combined mechanism. Okay, so if we combine sum of all mechanism, then it is portal mechanism. But if we combine all of them, then we have full combined mechanism. Okay. Back to the previous example. This one we have n equal to 5, I equal to 3, and n equal to 2. Then for beam mechanism, we have with using the work equation. Okay, so I assume that you really understand this, so I will move very fast. This is work equation. Then by using this equation, then we have lambda equal to 2.67. Okay, if you already understand, then just continue. If you confused, then just stop and check why. Okay, so lambda with this beam mechanism, we have lambda equal to 2.67. For panel mechanism, it is panel mechanism. Then we also develop the work equation. Okay, this is work equation corresponding to panel mechanism. Okay, then by solving this equation, we have lambda equal to 4. Lambda equal to 4. So solution here corresponding to panel mechanism, and this one corresponding to beam mechanism. Now, combined mechanism. Combined mechanism means we combine between beam mechanism and panel mechanism. We have because only two independent mechanism, then there is full combined mechanism. Okay, full combined mechanism. Then with this combined mechanism, we can develop the work equation for combined mechanism. WE equal to 2 lambda, and this is external work, okay? External work 2 lambda multiplied by 10 theta, and 3 lambda multiplied by 10, here 3 theta, okay, and equal to 10 theta. That is external work, and internal work equal to internal work equal to 20 multiplied by 6 theta. 1, 2, 3, 4, 5, 6. Okay. Then by solving this external and internal work, okay, external and internal work, then we have lambda equal to 2.4. 2.4. This is the solution of combined mechanism. Combined mechanism, and of course it is correct solution. Okay, correct solution. Now I will show you another way to determine the correct solution using the independent mechanism. For beam mechanism, okay, then we have external work is 3 lambda, 3 lambda, 3 lambda, and for internal work we have 80 because 20 here multiplied by 1 and 2 and 3 and 4, so we have 80. Okay, so this has theta and it has theta, then it's neglect. So for beam mechanism, and similarly we have for panel mechanism. We have 20 lambda for external work, and again 80. Then combine mechanism, we have 15 lambda, 50 lambda, and 160, 50 and 60, 160 cancel hinge at B, because when we combine two mechanisms, then the hinge at B is neglect. This is it is minus, okay, minus, and it is plus. This one is plus theta. This is minus theta, and plus and minus, then it disappear. Then hinge B minus 2 multiplied by 20. 20 is MP, okay, and 2 is 2 angle. Then we have the combined mechanism. We have 50 lambda and 120 lambda. Then finally we have lambda equal to 2.4. That is final solution. So you can use this procedure for your analysis, okay, for the analysis. Okay, let me give you an homework. The homework today is determine the load factor lambda and do the moment check of this structure, lambda and moment check. Okay, this is homework of today class. Thank you.